TSP, BRT operations. I'm part of the Center of Excellence, and I'm a leader at MIT. For those of you who were here last year, this project was not presented because it's like new for this year. So that's why I'm gonna talk a little bit about some background, why I'm motivated to do this project, the objectives that I have, methodology I'm using, the evaluation is closed, and then an example of one of the case studies that I'm doing. So I'm pretty sure most of you know what transit signal priority is, but just so we are clear on this, it's a really good technique at the operational level to provide priority to buses from traffic lights. The main idea is if the bus is approaching, we communicate with the traffic light, so we either provide the green early or skip the red, stuff like that. So we give the right of way to the bus. And it's been found to be really good at reducing travel times and improving the service bus reliability. And we believe that when it is properly designed with BRTs, you can complement all these other features for a better performance. So there are two different types of priority. There is either unconditional priority, where when the bus comes, it gets priority all the time, and then conditional, so if the bus is running late, for example, we provide priority, or if it has a certain amount of people inside. And the main idea is to extend the green, to do an early start on the green, skip a phase, or insert an extra phase so the bus can keep going. And in general, many studies have found that it's really good on time reduction. It can be found about 0.42% travel time reduction for the buses. But of course, as the bus benefits from this, the traffic is going to be affected. The cross traffic is going to be affected negatively. And so that's sort of the main idea on how to work this, and also try not to affect the traffic light synchronization that much. So that's a challenge that I'm working on for BRT specifically. As you know, BRT have different characteristics than the regular bus systems, and so we have higher frequencies, we have higher demands, and so that comes together for TSP to be more difficult to apply. And there's a lot of work on TSP done on conventional corridors, but not much has been found specifically for BRT. I've found a couple of papers, like one in Beijing where they were doing schedule-based TSP, and then another one in Lincoln City where they were using mostly speed guidance and advanced detection. But there are a lot of challenges that need to be considered, and they're probably corridor specifics. So what I'm really doing, besides reviewing all the extensive literature that exists on TSP, is really figuring out, how's the best way to apply TSP for a specific BRT corridor. We have different levels of demand, we have different levels of frequency, and I'm trying to evaluate a certain gamma of characteristics to get more conclusions on what works best on each scenario. And so I am evaluating different TSP conditions, conditional conditions, for depending on schedule, the certain load that the bus has, and on the specific intersection and the characteristics that it has and the traffic that goes through. And my goal at the end for my thesis and for this project is to develop a guideline on what would be the best way to apply this depending on the characteristics of the corridor. So I'm getting real data from transit agencies and the DOT. So I'm doing simulation experiments of a couple of corridors for comparison, and I'm getting APC data and AVL data from the transit agencies, and then I'm acquiring the signal timing plans that the corridors have, and either traffic count studies or an OD matrix from a planning model, and then the specific vehicle specification from the transit agency. So I'm trying to sort of put everything, trying not to make so many assumptions and try to put reality on the simulations. So eventually we can just sort of project them. And so, you know, I don't think I need to explain this. This is sort of how I'm preparing the transit data for the simulations. One thing I want to point out is the dwell time model I'm using. So if there's no, because in simulation experiments, the passengers are not really modeled, more like the dwell time effect. So this is like the most important part on the transit modeling part. And so when my dwell time model has two parts, if there is no crowding on the bus, then it's just at that time plus the time for boarding and alighting. But if there is crowding, there's some penalty per passenger, and so that's what I'm using. And it all depends on the qualities of the fleet, capacity that time is there, and it's city specific. So this project I'm only considering green extension, direction equation, and phase skipping. I'm not considering inserting a phase. And so what I'm really looking at is a couple of things. So first, I want to see what happens, because we care more about buses than cars. So we want to know what happens if we always provide schedule deviation, the schedule deviation condition. So every time the bus is there, we provide priority. But also, I want to see what happens if we do it combined with a minimum passenger load. So the bus needs to be running late and also have, 40% of the seating capacity completed. I'm also looking at, okay, what happens if I just do the schedule deviation, and if the intersection is critical, then we do not provide any priority. As for those of you who've been to Boston, we have the example of Mass Ave and Washington Street. They're both really critical intersections. And so if we provide priority to one way, the other way is going to be critically affected. And so maybe the benefit won't be worth it. So I'm also comparing that, and then also doing the load constraint only on the critical intersection. So I'm sort of playing with different combinations of priority to see what works best depending on the corridor characteristics and specifically on the intersection that we're analyzing. And I'm looking, how the travel time changes, what's the impact on the bus speed and the traffic speed, the intersection delays, crowding, and I want to also look at vehicle emissions in the long run. So I have 3 case studies. I have one in Boston, which is the Silver Line 5 in Washington Street. I have one in Minneapolis, about 10 Central Avenue, and I did one in Santiago this past summer/winter with Carmen Avenue. So these are 3 very interesting corridors, because they're sort of different in headways. One has 4 headways on the peaks, 6 minutes. Another has 12, and then on the ridership, for example, Central Avenue has 7,000 weekday boardings, but then the others have about double of that. So sort of looking at different demands and different headways to sort of get a more insight of what's the best strategy. And for the Santiago corridor, this is really interesting. It's very different from what we have in the U.S., so I think this is going to give us a lot of insight for Latin American corridor. So it's really good I have it, and eventually what I'm going to do is project them. So at the end, I want to know what will happen in 10 years and what would be the best strategy if we have higher demand and a lower headway. And so I have some results, but not for comparison yet. But it's looking really good. We have the insight that we needed. We're getting benefits on the travel times. And so this is just an example of why we need to change the conditions that we have. For example, in Boston, we already have TSP on a couple of intersections. But looking at the on-time performance, without TSP on the peak times, it looks as it's better when we have TSP on the peak time. So sometimes the way we apply TSP is not really good. So this sort of motivation on this corridor and why we need to improve the investment that we already have here. And so now I'm on the step of analyzing all the results and sort of getting insight on the guidelines that I should generate. So thank you very much.
Thank you. Tony?
Very interesting topic. I'm certainly here just to raise you more problems, not solutions. But one suggestion in this case is for you to look at the Curitiba case, because Curitiba has just introduced traffic signal for buses, but for certain services, because we're talking about 1 minute headways or even less than that, so you cannot provide to everyone. So they did overtaking and also signal actuation. So I think it would be an interesting case, because in most cases we have in Latin America, we're talking about frequencies of very high frequencies, and suddenly that could be applied perhaps to certain buses. In Curitiba they are using for the mega buses, which are really very, very big.
Yeah, so that's going to be a more complicated thing. I think it's really interesting. The main problem when doing this is acquiring the data. So it's good here that we have many contacts. We can sort of get it quickly.
Yeah.
So we can
No, I understand that. Just forget to raise another issue.
Of course, if you have sort of data that we were in contact that I can get, then that would be great.
I'll give you my card and see what you can.
Are you, to me, how would you use TSP to get the schedule right? Because at least in cities with high frequency, the schedule doesn't make much sense.
Right. So maybe more even headways. So and try to get less bunching. So if the bus is running, then you provide priority, but not if it's early.
Okay, fine. And how are you considering to implement TSP to prevent bunching? Can you give us an idea?
So what I'm doing is just considering on the schedule deviation and on the load condition. So at the end, that's going to be affected by the dwell time. So it should, what are the results I'm looking, it is improving the headways because we are not keeping the buses together. The priority goes to the bus that is running late, so it sort of evens them out a little bit. But specifically on how it's going to improve bunching severely, I still don't have the answer to that, but I'm going to run my results.
My question is the reverse of what Don Carlos said. Holding a bus intelligently is not signal priority, but that is part of an approach to controlling bunching, number one.
Right, that would be something separate.
Number two, something that I've talked to Dario quite a bit about over the years, that once you get to a headway of once a minute, as tight as your signal spacing is, traditional ideas about signal priority that might work in America, Australia, or Canada, where you're never going to see better than a 5-minute headway, that kind of TSP goes out the window.
Yeah, so there I think the point goes to selecting to which bus we're going to provide priority.
Well, but it may not even be that. It may be a totally different strategy. Because I used to ask him about Avenida Caracas. He said, well, what we try to do is what we call passive signal priority, which basically is run synchro or something like that on the basis of bus schedules rather than on the basis of the velocity of cars in the corridor. So what I'm suggesting here is that maybe rather than just approaching the low-hanging fruit, which I think is a situation on the Silver Line in Boston or a not very busy line in Santiago, it would be very good to see a situation like you would see in a Sao Paulo corridor perhaps, or
in Curitiba,
where the intersections are overloaded with buses. And I don't think a strategy that says, well, you just give them to every 10th bus or you give them to express buses, because in a busy BRT system, I'm not sure you're differentiating.
I'm sort of including that on my project because I'm projecting my cities, and so the corridor in Santiago, which has 4-minute headways, will eventually eventually be projected to a higher demand and a higher frequency. So I will be analyzing what will happen if we have higher demand.
But be conscious of the fact that this may not be a scalable thing. In other words, what you do in 2 minutes may not be more of the same. It may require a completely different logic than you built into your simulation.
Yeah.
Now, I just suggest that given that there are many, many applications of 5-minute frequencies or 4-minute frequencies, this is targeted there, and not to solve within your project, but to identify eventual things that need to be done that are applicable to these orders. So you don't need to solve all the problems, but you recognize very well which are the problems that may arise in much higher frequency corridors that we need to deal with. Brendan.
Okay. Now, a different issue in TSP is where the bus stop located, because when you have a bus stop very close to an intersection, sometimes the prediction of the arrival of the bus to that intersection is perturbed by the amount of passengers that load and unload at the bus stop. So what are you doing with that, and how it's taken care
about
of?
that on a couple of papers, because if the intersection is too close to the bus stop, it's going to be stopped anyway. Really, my corridors don't really have that right now, so that's sort of a benefit from what I'm doing. But I think it's much easier if you do need the TSP to have better reliability. Maybe move the bus stop. I think that would be cheaper.
10 years ago, there was a paper that was in an ITE journal done by someone that worked for IBI Group in Vancouver, where they analyzed using VSIM the application of TSP. It was done for the 98 the rapid bus line, whether you have the stop before or after the intersection. I assume that's what you're looking at. And I think it was fairly unequivocal that after was a lot better under any set of circumstances. I wish I had the paper that I could share with you. You know what I'm talking about?
With that again, we can't necessarily have hafter all the time, right? If you want to have one bus station for both sides, then that depends.
Yeah, if you have split, you
Yeah.
have split platforms. The center platform, you can't mess it up easily.
There was an intervention by Brendan Fee.
Okay, a few points, I keep it brief. I recognize your research is probably focusing on a specific thing which sits within the context.
Yes.
So I think when you start to move it beyond a very specific research focus, you must take into account the broader operations management context for the transportation service, but you must also take into account the broader traffic management context that the city is doing, because what you do for the bus has an impact on the rest of the traffic, and you also have to actually get the traffic engineers and the roads authorities on site. I believe in Joburg, for example, that has been an extremely difficult issue to date. Second thing is there's a wealth of research like this from the early and mid-90s in the EU program, particularly Drive 2 and so forth. And I think quite often it's felt, oh, that was 20 years ago, that can't be any use. What we're doing at junctions today is the same as what we were trying to do at junctions 20 years ago. Technology has moved on a little bit, but the traffic stuff we're trying to do is actually just as relevant. I can give you some assistance in finding where some of those reports would be. They were very, very extensive multi-city projects. Third point is, when we get down to BRT utilization and we get into intense activity, I think this is where we have to decide, is the junction, is the TSP trying to be active and participate in the management of the services, or passive? Just don't get in the way. So all we want to do is to know that we can get through the junction without disturbance, and we don't expect it to do any more than that. Now that's still a major challenge, but it's a different approach to where we're trying to integrate it into part of the active management of the route. And the fourth point is, in terms of the intense situations, where we get to BRT, I think you have three contexts. One is where you have a single route running at very high intensity. There, the headway management is extremely important. The second is where we have very intense operation, but on multiple routes, whose individual headways might be 4, 8, 10 minutes. And that is a completely different situation. It's more a capacity management, where you have at least some more flexibility in the headway management. And the third is where
things are actually happening at that junction. You've got left turns, right turns, you've got buses joining and leaving. And that is a very different and even more intense situation than where you have a lot of buses, but they're all doing the same thing going straight through. So that's just some feedback to help you
Yeah.
extrapolate or expand your research.
We'll be able to cover everything on my research, but definitely next steps.